So we have seen, already discussed for the overcurrent relay coordination based on time discrimination, based on current discrimination, and there are some disadvantages for only this time discrimination and only this current discrimination. We have already discussed in two previous videos. Today's topic is the overcurrent relay coordination by both the time and current discrimination. So let's start. Okay, so for time current discrimination, time and current discrimination, we will be familiar with the overcurrent relay, which is 51. The ANSI device number is 51. This 51, what is 51? 51 is IDMT. So what is IDMT? This is inverse definite minimum time. Inverse definite minimum time. So here, with the help of this IDMT characteristic of this relay, we can overcome the problem related to the time only discrimination or the current only discrimination, because this is the combination of both the time and current discrimination. Let's draw this curve. Let's draw this curve. The typical IDMT characteristic is like this, and obviously this side is time t and this side is current I. So this is the inverse characteristic. This is the inverse characteristic. But this is not actual IDMT. Inverse definite minimum time. This is not IDMT curve. This is only inverse curve, because you can see from here, from this point to this point, this is the inverse characteristic. And if we talk about the IDMT characteristic, then from this point, this curve will lose its inverse characteristic, and this will be like this. This will be DT characteristic, definite time, with this time discrimination. So that means this part is inverse and this part is definite time. So this is the combination of this inverse characteristic as well as definite time characteristic. So what is about this point? This point is defined when this relay characteristic will lose its inverse properties and the definite properties will begin. For some manufacturers, it depends on the manufacturer, relay manufacturers. For some manufacturers it is 20 times or 30 times or 50 times of the current. So at reaching at 20 times of current, or at 30 times of current, or at 50 times of current, the relay characteristic will lose its inverse properties. After that it will enter in the definite time region. So this is the IDMT characteristic. More specifically, let's check with the help of IEC. Let's show you one thing here. This is as per IEC 60255. As per IEC 60255, there are different types of inverse. There are different types of inverse characteristic, IDMT characteristics. One is standard inverse. Another one is very inverse. This is extremely inverse, and this is the formula. Time t equals to TMS. TMS is the time multiplier setting multiplied by 0.14 by IR to the power 0.02 minus 1. So if we choose this standard inverse characteristic, then it will follow this equation, and the curve nature will be plotted following this equation. So this is time multiplier setting. I will discuss in detail in subsequent videos. Also, I have prepared the videos with the help of ETAP software for the protection coordination video. You can check out that video also. Very inverse. For very inverse, T equals to TMS multiplied by 13.5 by IR minus 1. It will follow this very inverse curve, will follow this characteristic. Next, extremely inverse. This T equals to TMS into 80 divided by IR square minus 1. IR square minus 1. Let's show another example. This is one of the project example. Here this is the fault current, calculated fault current, and PSM. Here is the PSM plug setting multiplier, and here is the operating time. This is the operating time. You can see the formula here. This is standard inverse. IEC curve. So here is the formula: 0.14 multiplied by TMS divided by IR to the power 0.02 minus 1. Whatever we have seen here, this T equals to TMS into 0.14 by IR to the power 0.02 minus 1. So it will follow this equation for the standard inverse curve. Now let's go back to our discussion point here. So whatever we have seen, we have seen standard inverse or normal inverse, very inverse, and extremely inverse. So if I plot here, these three curves, probably this will come like this. If we select standard inverse or normal inverse, the curve will look like this. Okay, for very inverse, For very inverse, the curve will look like this, and for extremely inverse it will follow this path. So based on the equations, standard inverse, very inverse and extremely inverse, this will follow. So with the help of this characteristic, we need to coordinate with the different protective devices. So based on the downstream network, based on the downstream protection system, we need to choose which curve to select, either normal inverse or very inverse or extremely inverse. Which curve to select, we need to choose. Suppose the downstream protective, coordinated downstream relay characteristic is like this. If I show in dotted line, if it is like this, then definitely this normal inverse will not be applicable, because here is the crossing, and also probably due to the fouling here with the very inverse curve, we cannot select this very inverse curve as well. The only thing we can think about this extremely inverse, because there is a gap between these two. Because if we tell that this is the LV circuit breaker or the LV protective device, and this is the upstream relays, then this extremely inverse curve, IDMT characteristic curve, will be suitable for this particular case. So we cannot select this standard inverse or normal inverse curve or the very inverse curve. So this depends on this. Let's give one example. It will be clear. Suppose for a motor, let's draw one curve again. Suppose the motor characteristic curve, is like this. So this is the starting curve. This is T, this is I, so time current characteristic curve, and here this is the starting current. So up to this we should avoid the upstream circuit breaker coordination or the relay coordination. So suppose the standard inverse curve, if we select the standard inverse curve, it may be like this, or the very inverse, if we select IDMT very inverse, it may be like this, or if we see the extremely inverse, if it comes like this. So in that case we cannot select this one, because there is a clear fouling. So during the starting of the motor, this relay will pick up and probably the circuit breaker will trip. So in that case, if we select this characteristic, this is standard inverse, it may be suitable. So based on this, based on the downstream network motor connection, the motor starting current, or the downstream network relay coordination, we need to select which IDMT curve we need to choose, whether it is standard inverse, whether it is very inverse, or it is extremely inverse.